Okay, so I'm going to try to record this set of notes for you so that you can hear me talking through everything, and hopefully this will go well. We'll give it a shot. We're starting our chapter on simple harmonic motion. You deal with simple harmonic motion, again, all the time, even though you don't realize it. When you sit down in your car, the seat of your car has springs. They tend to vibrate up and down or bump you up and down if you hit a big bump. If your shocks are not very good so that that motion gets absorbed, you continue to bang around for a while. You used to have ink pens that you had a spring and you would push down on it, and that would push the cartridge out so that you could write with it, and then you could pull the cartridge back in by releasing the spring. So there are just all kinds of things that happen with springs that we need to be aware of. So we are going to see what happens with this lovely little PowerPoint. Okay, so here's a jumper on a trampoline, and he is exerting a restoring force, or experiencing a restoring force, because the jumper is going to jump down. The trampoline is going to push back up on him and bounce him up. And the amount of force that the jumper receives is directly proportional to the average force required to displace the mat. So the harder he jumps, the higher he's going to rise. Such restoring forces provide the driving forces necessary for objects that oscillate with simple harmonic motion. So that's not a big deal. That makes complete sense. After finishing this unit, hopefully you will be able to write and apply Hooke's laws for objects moved in simple harmonic motion, and we'll do that lab on Tuesday. You will be able to write and apply formulas for frequency, period, velocity, and acceleration in terms of displacement x or time t. And I'm going to stop for just a second. So none of those symbols are new to you, are variables. Frequency we have always called f. Period has always been capital T. The velocity is v, as always. Acceleration is a. We used to call this d, but we're going to call it x because we're going to talk about along the axes the displacement that happens, and time is just simply t, so that's not a big deal to you. And we should be able to describe the motions of pendulums and calculate the length required to produce a given frequency. So those are our objectives for this unit. And again, if you need more time, have the sub pause the movie for you. Periodic motion. Well, let's get rid of this. So, simple periodic motion is that motion in which a body moves back and forth over a fixed path, returning to each position and velocity after a definite interval of time. So things just move up and down, and we call that periodic motion. So the amplitude is the distance from the rest position to the highest displacement. You can have a positive amplitude. You can have a negative amplitude. Simply the direction, not a big deal. And if you think about it, as this motion occurs, up and down, it's really nothing more than a circular motion. Because as this goes down, it reaches the lowest point, it begins to come back up, shoots past its rest position, keeps going, reaches the highest point, returns to its rest position. We already know frequency is 1 over period. You learned that with circular motion. And you know those things already. I don't really think you need to copy them. But if you do, have the substitute pause the video for you. Okay, example 3, example 1, hello, says that a suspended mass is going to make 30 complete revolutions in 15 seconds, and it wants to know the period and the frequency. Well, what I know is that my period is the amount of time that it takes for 1 revolution. So, and my frequency is the number of revolutions per second. So I should be able to, if my pad is going to write. So let's see if that's going to work. Let me pause it and see if I can get this little rascal to write. Okay, things are good now. So I know that it's going to make 30 cycles every 15 seconds. So that's 2 cycles per second. And we call that 2 hertz. That's your frequency. If I want the period is 1 over f. So I have 1 over 2. So 1 over 2 cycles per second, the cycles fall out. So 1 over 2 seconds is going to be 0.5 seconds for the period. Okay? All right, well, let's to see if the PowerPoint agrees with us. So if we go over here and continue our PowerPoint, there is our period. It agrees. And there is our frequency. So life is good. Not a big deal. Have someone pause if you need to have a little more time. All right, so Hooke's law has to do with springs. So when a spring is stretched, there's a restoring force that is proportional to the displacement. So if you think about it, if I pull down on this, doesn't the spring want to pull back up? So that is my restoring force of the spring. I apply a force to pull it down. As soon as I release it, the spring pulls it back up to restore it to its rest position. So there's my equation. The spring constant K is a property of the spring, so it depends on what it's made out of. K is equal to delta F over delta X. I'm going to go back because I want to talk about that negative sign. That negative sign right there simply tells me that, well, if I can mark with this thing, simply tells me that it is a restoring force. And it's going to act opposite direction of the motion. Okay? That's all it is. Not a big deal. And I don't typically even carry that through when I do my math. I just know that it's a restoring force. It's going to try to change that motion, take it back to equilibrium. Okay, so the work done in stretching a spring. Work done on the spring is positive. I pull it down and stretch it. The work done by the spring is negative because the spring is trying to restore itself. To stretch the spring from x1 to x2, I'm going to say the work is equal to 1/2 kx squared minus 1/2 kx1 squared. If I go back, which I will, this is a graph of force versus distance. We learned several chapters ago that when you have a graph like this, the area under the curve there is the work done. So I can maybe roll this down a little bit. Yeah, there we go. So I'm really talking about this area right here. So I could split it into a triangle and a rectangle if I needed to get the work done. That's the formula for it. That is how the area under the curve can be useful to us. All right. So example 2 says you have a 4 kilogram mass suspended from a spring and it can produce a displacement of 20 centimeters. What is the spring constant? So if I look at the math, I know that K is equal to F over X. F is 39.2 newtons. X is the displacement of 0.20 meters. So there's the spring constant, 196 newtons per meter. All right. So that was not a big deal. Part B, the mass M is now stretched a distance of 8 centimeters and held. What is the potential energy? Potential energy is equal to the work done in stretching the spring. So there's the work done. It had no potential energy initially because it wasn't stretched. So the work done is simply going to be the final potential energy, which is 1/2 kx squared. And if I do the math, I get 0.627 joules for my potential energy, which is also the work done in stretching the spring. And again, if you need more time, pause is the best thing to do. All right, displacement in simple harmonic motion. So we're going to call our displacement positive when the position is to the right of the equilibrium, which is right here. And we're going to call it negative when it's located to the left. The maximum displacement is called the amplitude. Remember, we just talked about that in the other picture. We had a picture where you had the block right there, and it was just hanging. That's the rest position. So if it falls all the way down, that's the amplitude from here to here. And if it rises all the way up, that's the amplitude from here to here. So this is the same exact thing, it's just done horizontally instead of vertical. Not a big deal. Okay, so anything to the right, positive, anything to the left is negative. When I've taken it as far possible to the right or as far as possible to the left, those are the amplitude points. That's our maximum amplitude. Okay, my velocity, positive when it's to the right, negative when it's to the left. It is 0 at the endpoints and the maximum occurs in the middle. This is huge. So let's see if we can pull it down a little more. 0 at the endpoints because it has to come to a stop here and here, so it can then go back that way. Got to reverse its motion and head back to the center, but it can't if it never comes to 0. The fastest speed occurs right there. So that's where KE is max. This over here would be where PE is maxed out, and I guess it's actually right here in this graph. So here's where PE is max because there is no kinetic left and it's all stretched as far as possible, a distance called A. And then PE would be max over here on the right-hand side because, again, it's stretched as far as possible. It's come to a stop. There is no KE. There is no KE here. And this is all KE and no PE because there is no stretch left at the center. So again, if you want to get that down, pause it. And make note of that because, man, it sure will be helpful in a little while. Okay, now we want to look at the acceleration. Well, you have to look at the force to figure out what's going on with the acceleration. Okay? So acceleration is in the direction of the restoring force. A is positive when x is negative and A is negative when x is positive. Okay? So think about that. The acceleration is positive when x is negative and negative when the x is positive. The maximum acceleration occurs here. So let's get our pen. A max is here. A max is here. And that should make sense because that's when the force is the greatest. The greater the x, the greater the f. So if force is greatest, that's when acceleration will be greatest. If force is 0, which it is right here because it's at the equilibrium position, then A has to be 0 there. Okay? So the big trick to getting those directions right is that the acceleration is in the direction of the restoring force. It's accelerating back in that direction. And that makes sense because it's got to come to a stop and then accelerate back to the middle. Has to come to a stop and then accelerate back to the middle. So if you think about it in terms of the forces applied and what's going on, it makes a whole lot of sense. Okay? No acceleration here because there is no force. Maximum here, maximum here. It's accelerating back to the right, so we call that positive. If it's over on the right-hand side, it's going to accelerate back to the left, so we're going to call that negative. Again, stop the video if you need a little more time. Okay, so let's look at this one. This is example 3. It says you have a 2 kilogram mass. It hangs at the end of the spring. We know the spring constant is displaced 12 centimeters and then it's released. What is acceleration at the instant that it is 7 centimeters from the rest position? Okay, so if F equals ma, which it does, then F is my, could you plot right here? F is my restoring force, and it's equal to Kx. But I know that F is also ma because of Newton's second law. So A is equal to Kx over m. And I'm not going to worry about that sign. I'm going to figure out that sign once I get it done. Okay? So I took the 400 newtons per meter times the 0.07 meters and divided by the 2 kilograms. It is at a position of positive 7 centimeters. Okay, so if it's at positive 7 centimeters, then it's being accelerated back that way, so that's where the negative sign came from. All right, pause it if you need to. Okay. So there's a little note right here that says when the displacement is positive 7 centimeters, which means it's down, the acceleration is negative 14 meters per second squared upward because, again, the acceleration is going to be in the direction of the restoring force and the spring is trying to pull it back upward. Okay? So that's why the displacement is opposite direction of the acceleration. All right, what is the maximum acceleration for the 2 kilogram mass in the previous problem? They give us our amplitude is 12 centimeters and our K is 400 newtons per meter. Max acceleration occurs when the restoring force is maximum. So when I have the greatest amount of stretch or compression. So F is equal to K, negative Kx. So if I'm looking for my maximum acceleration, that's going to occur when my displacement is maximum, so that's a positive or negative amplitude. Remember, amplitude is the greatest displacement from your rest position. So it occurs at plus or minus 12 centimeters or 0.12 meters, so I can solve for my A. and it could be plus or minus 24 meters per second squared. The plus or minus is because it can occur here or here. And if it occurs here, it's headed that way, and if it occurs up here, it's headed that way, opposite direction. All right, now again, we have our friend conservation of energy. So the total mechanical energy, which is PE and KE, has to stay the same. So for any 2 points A and B, we may write that conservation of energy equation: kinetic, potential, kinetic, potential. And again, you probably need to pause and have some time to write that down. The period and frequency as a function of A. So for anybody undergoing simple harmonic motion, I have those expressions right there. The frequency and the period can be found as the displacement and acceleration are known. Note that the signs of A and X will always be opposite. And if they are opposite, then that will help me to get my square root to come out to be a positive number. So 1 over 2 pi squared of negative A over X. So I have negative A, positive X, and then T is 2 pi squared of negative X over A. So make sure that you get those equations. X is your displacement, A is your acceleration. Now, period and frequency as a function of the mass and the spring constant.